Today we're going over 7.6 function operations. So let's say we have the two functions of f of x and g of x, where f of x is 3x plus 8 and g of x is 2x minus 12. So if we're finding f plus g, that simply just means to find f of x plus g of x. So we're going to plug in. So we do f of x is 3x plus 8. So we write, instead of f of x, we write 3x plus 8. And instead of g of x, we write 2x minus 12. And then we combine our like terms. 3x plus 2x is a 5x. 8 minus 12 is a negative 4. If we're doing f minus g, then that just simply means f of x minus g of x. So for this one, f of x is 3x plus 8 still. And we're going to minus, we have to put this in parentheses to show that we're subtracting all of g of x. So we subtract 2x minus 12. And the reason why we have to put this in parentheses is because we have to distribute the negative to every term here, because we're just subtracting the entire g of x. So this will give us 3x plus 8 minus 2x plus 12. Because we have a minus 2x minus a negative 12 is a plus 12. Combining your like terms, 3x minus 2x is x. 8 plus 12 is 20. If we're finding the domains for both of these, there's no restrictions on either of them. So the domain for both of them is all reals. The only time you would have a restriction on your domain for these is if you have something in the denominator, it cannot be 0, or if you have a square root, you cannot have a negative. So let's move on to multiplication and division here. So let's say we have f of x is equal to 6x squared plus 7x minus 5, and g of x is equal to 2x minus 1. So if we wanted to do f of x over g of x, we'll plug that in. F of x is 6x squared plus 7x minus 5, and g of x is 2x minus 1. So we need to factor the numerator, and then also for the domain, before we go ahead and cancel anything, we have to say that the denominator, which is a 2x minus 1, that cannot equal 0. So you take whatever is in the denominator and you say that cannot be 0. So you get a 2x cannot be 1, or x cannot be a half. So therefore your domain is going to be all reals except for a half. And we just did that by setting the denominator and saying that cannot be 0. So to factor this, the numerator, we have to do a times c, that adds up to b. So a times c, your a is a 6, and your c is a negative 5. That's a negative 30. So we say what multiplies to negative 30 and adds up to positive 7. That's going to be 10 and negative 3. So we know that when we're doing this, we will replace our bx term, our 7x term, with 10x minus 3x, because it's actually the same thing. But when we are factoring this, it'll be easier. This will allow us to factor it. So we say, what can we take out from the first two? The first two I can take out a 2x, and I'm left with an x plus 5 for this one. Sorry, a 3x plus 5 when I take out a 2x. And for this one, I have to have the same binomial left over, 3x plus 5. So I'm going to take out a negative 1 from this. So we made both of these binomials, both of these terms have a 3x plus 5, so I'll take that out. And I'm left with a 2x minus 1 here. And that's how I factor it up top. So the numerator is therefore 3x plus 5 times 2x minus 1. And in the denominator, I have a 2x minus 1. I'll cancel those, and therefore I'll be left with a 3x plus 5. And that is f of x divided by g of x. Okay, moving on to the composition of functions, we will have, for example, if something is written as g of f of x, that can also be written as g of f of x, where you're going to first evaluate the inner function, and then you're going to use that answer and use that as your input for the outer function. We also have f of g of x. This is the composition of functions, not multiplying. And this is f of g of x. So for this one, you would first evaluate g of x, whatever you get for that, then you'll plug that into f of x. And these are called the composition of functions. Okay, so we can try one here where we have, for example, g of x is equal to 2x, and we could say f of x is equal to x squared plus 4. So let's first do g of f of x, which is the same as writing g of f of x. So we will first replace our f of x with what it's equal to, which is x squared plus 4. So we have x squared plus 4 here, and all I did was said f of x is equal to this, so I'm going to replace it. Now I need to find g of x squared plus 4. So here I have g of x. So I'm going to replace this x with this whole thing. So I have 2 times whatever x is. And I'm going to put in x squared plus 4. Distributing in your 2, you get a 2x squared plus 8. So that's our g of f of x. Okay, now we'll go the other way. Since the composition of functions is not commutative, we're not going to get the same answer. The only time we will get the same answer is if these are inverses, and we'll get into that later on. So now we'll do f of g of x, which is the same as writing f of g of x. So we first plug in g of x. So we replace g of x with what it's equal to, which is a 2x. And then I'm going to take f of x, I'm going to replace x with 2x. So I have 2x squared plus 4, which is equal to 2 squared is 4, x squared plus 4. And that's how we solve the composition of functions. If we wanted to solve it using a number, we can also do that. So we'll do another one where we're using a number. So let's say we have f of g of negative 2. So what we're going to do here is we'll first plug in negative 2 into your g of x. So we have f of 2 times negative 2, which is f of 2 times negative 2 is negative 4. And then you're going to plug negative 4 in for your x in f of x. So you replace x with negative 4. So that will be a negative 4 squared plus 4, replacing the x here with negative 4. Negative 4 squared is a 16, plus 4 is 20. So f of g of negative 2 is 20. And that's how you do the composition of functions.